Welcome, this is June 2014 AQA, actually AS, for Physics A. Now, as I uploaded quite a few of these videos last year, two papers to uploaded actually, and obviously I've just got around now to finish on with the rest of them. So anyway, let's kick off. So K+. So what is a quark structure of a K+? This is a positive kaon. Now, we have to think what a kaon actually is. Okay, so we have obviously you have the leptons and the hadrons as two main particles. So the leptons, obviously, fundamental particles, so there's nothing smaller. So obviously, therefore, this is a hadron. Now, because this is a kaon, or a K-meson, this is known, obviously it's part of the meson group. Now the meson group consists of obviously the kaon, the pi meson, and the sigma meson, I think. Anyway, so what all mesons have in common in terms of the structure is they have a quark and an anti-quark pair. So what we mean is it might have a strange and an anti-strange, for example. Obviously it would never have that, but that's just a bit of an idea, okay? Right, so we have to think, what are the properties of this before we start delving into the types of quarks we can use, which are obviously the things that make up these hadrons and, hadrons, so the mesons and the baryons. Okay, so to think of that, we have to go, okay, well, they are a quark and anti-quark pair, so that's something we know. We also know this particular one is positive. Now, the fact it is a positive has bearing on charge, obviously. So obviously it's going to have a positive charge, and it's going to have a positive charge of 1. It's not going to have a charge of positive a fifth, because life doesn't work like that. Well, maths does, but this is physics. Anyway, so it's got to have a positive charge. Now, it's got to be a quark and an anti-quark pair. So thinking of that, just go back to I'm just going to label the quarks now. So the way I think of it is, so you've got up, charm and truce. So these are sort of thinking of, so you could, I'll explain in a minute. So up, charm and truce, they have a positive charge of 2/3, and down, strange and bottom, beauty, sorry, down, strange and beauty, they have a charge of negative 1/3. So obviously to make up a third, we've got to have one of these 2/3 and a anti-particle of this. Now we're told in the question that it's got a strangeness of +1. Now you should know from your formula book, the strange particle has got the actual strangeness of -1, and that can change in an equator decay. But it's not decaying, we're just asking what is a quark structure of this. So therefore it's got to be an anti-strange particle, because the strangeness of 1, a positive one has to be an anti-strange particle, because there's no other particle that is strange, so therefore we know that's got to be one of them straight away. Okay, so if we add that charge, that's positive third charge, so we need something from this side of the column. So we need something that's got a positive charge of 2/3, but is not going to affect the strangeness. Now, obviously therefore it's going to be up, or U, anti-strange, up quark and an anti-strange quark. Okay, so a charm, couldn't really use a charm, or you can really use a truce either. Okay, so hopefully that makes some kind of sense. If you want me to go into more detail on why as I guess you could have used truce or charm, but I just used up. Okay. The next question says, what is the baryon number of the K+? Now, people might start going, okay, well, baryon numbers, well, it's a meson, so it's not going to be a baryon, so why would it have a baryon number? Well, it does, but why would it have a baryon number or anything other than 0? Because it's not a baryon, so you wouldn't give it a number that it isn't associated with it. So therefore it's got a 0 baryon number. Okay, 1A part 3, what is the antiparticle of the K+? Now, to understand this, we need to think of the other antiparticles. So the electron has got a negative charge, so therefore the positron has a positive charge. So one of the things that changes is the charge. Okay, that's the only difference between a particle and an antiparticle. They have the same properties, just opposite charge. Okay, so therefore 1A part 3 is just the K negative, or the negative K. Okay, that's all you need to write for there. So now it's only worth 3 marks, these 3 so far, one a piece. The next question, it's kind of got us going into a bit of a table. So we've got something like this. So I'm just going to shorthand write it. So we've got classification, so these are the type of things we need to look at. And then, okay, so actually we've got this equation, sorry. So the positive kaon goes into a muon neutrino, which is denoted by this, and a muon, a negative anti-muon. Now, the muon number, or the think of it like that because a muon is a lepton. The lepton number is the same on this side as it is on this side, and that is because obviously we've got 0 on this side and then a positive muon number and a negative muon number cancel out to give a total muon number of 0. Anyway, so what we've got here is we've got a obviously the positive kaon, the muon neutrino, and the anti-muon. Okay. So obviously the first line's already been filled out for you. It's leptons, and obviously K plus is not a lepton, but the other two are. Okay, as we said, fundamental particles, they are not made up of any quarks, so we couldn't apply this theory to a muon. Okay, and then the next one's quite easy. Is it charged? Well, obviously just look at the sign for that. The first one, yes, that is charged. The second one isn't, because neutrinos are always neutral. Okay, and the positive muon or the anti-muon obviously is. Just look at the charges, as I said. Hadron. Well, I just mentioned there. So hadrons are your leptons and your hadrons, and obviously if they're leptons, they're not going to be hadrons, are they? So you can give them, even if you didn't know what hadron was, you could cross them off. Okay, well, obviously the kaon, positive kaon, is a hadron. Because it's either a hadron or a lepton, and if it's not a lepton, it's going to be a hadron. Okay, and that's because hadrons are made up of mesons and baryons. The key difference between the two, apart from the structure, is that baryons decay into protons because that's the most stable baryon. Okay, right. I say the structure is really different. Anyway, next one, meson. Okay, well, it can be a meson and a hadron because the meson is just a subgroup of hadrons. So the kaon is a meson because it's a K meson. Right, and obviously these two aren't, if they are leptons, they're obviously not going to be hadrons or mesons, are they, if they're two sets of particles. Okay, so 1b part 2 says, in this decay, so that one was decays we're told, in this decay, charge, energy and momentum are conserved, standard things. Give one of the quantity that is conserved in this decay and one that is not. Okay, so well, obviously the baryon number is conserved because that cannot be changed. Well, even without looking at that, because they've told you how that works, so you just got to think, well, what laws are abided, even if you don't really have to read into this question too much. You just have to think, well, they've told us this equation works, so just use your standard laws if this equation confuses you. So the baryon number is conserved because obviously the hadrons, and then we've got baryons and mesons, so there's no baryons on either side, so the baryon number is obviously conserved. And then what isn't conserved? Well, strangeness, because it's the strangeness of positive 1, and this has a strangeness of 0. Okay, so they're two things that you can say. They're the two things I would go for. I wouldn't worry about trying to get into any other ones because they are nice and simple. Okay, so just get rid of that. So hopefully you've got that table down. As I said, it's online on the internet, so you're not the thickest people in the world. You should be able to get that. Okay, so it's given us the next one. It's given us this equation. So it's K plus decays into a pi plus and some other particle they've called X, and we're told to identify one of them from the following list. So it's either an electron, so that's this X particle, muon, a negative pion, neutral pion, neutrino, neutron, or positron. Now, to think about this, you have to think, okay, well, go through what we've literally just done there, but it's not giving you the help for it this time. So, you need to look at the conservation laws. Now, obviously, this equation is going to work. You've just got to make it work. Now, so what I'm going to do, instead of just telling you the answer, I'm going to go through each individual one and prove to you why it may or may not be the case. Okay, well, electron. Well, let's think about this. Electron is a lepton. There's no leptons in this side, and there would be an electron in this side. Now, granted, if we had X1 and X2, like such, then you could say, well, potentially, assuming the other laws are conserved, we could have an electron and an anti-electron. But as we've only got one space available on the right-hand side, then it can't possibly be an electron because the charge would not be conserved. Okay, so it's got to, obviously, because this is positive and this is positive, this has got to be neutral. Okay, so is it a muon? Well, no, and that's because a muon is charged, so we can't have a charged particle there as we've just discussed. Okay, so the next one is a negative pion. Again, we can't have a negative pion. A neutral pion, well, that could potentially work because, again, the charge, that solves our charge problem. We've got to also think, well, it doesn't consider the meson number, does it consider the baryon number? And it does all of them. A neutrino, well, that granted wouldn't have any charge, but again, that's a lepton, so we can't choose that one. So the one it's looking at so far is this neutral pion. A neutron, well, that's a baryon, and there's no baryons on this side, so we can't have that, even though it is a hadron. And a positron, well, again, it goes back to our idea of we can't have leptons, so that's the only one that you can have. Really, even without knowing the other facts like the lepton number, you could have just think, okay, well, it's got to have a, just by looking at the, if you didn't know anything about physics, and you could just think it logically, okay, well, this is positive, so obviously it's going to have to be neutral. And the only ones in there that are neutral are the neutral pion and the neutrino. Well, and the neutron. So you've got a choice of 3 there. Even if you weren't sure of the other factors, you've got a choice of 3. You've got a third chance of getting it right, 33.3% recurring of getting it right. So even if you didn't know the other bits, you can still have an educated guess. And is this pick one? You know, it's quite a nice one. That part C, part 2 just goes on from what we were just saying there. Give a reason. So you would just say the baryon number can't be changed, so we can't add another baryon there because there's no baryons on the left-hand side, and it can't be a lepton, and it has to have a neutral charge. So therefore, that's why you'd say, therefore it's a pi 0 meson. Okay, we don't have to say pi 0 meson. You could just draw that in your answer, and that would be acceptable. Okay, so hopefully that makes sense. That's question 1 from June 2014, Unit 1. Okay, so thanks for watching. Hopefully that's been helpful. Sorry, I'm just trying a few videos with this tablet instead of keep going back to my laptop all the time. It seems to be working out fine for me, so hopefully I've not making a mockery of myself all the time, though that happens anyway in life for me. So anyway, thanks for watching, and we'll see you in the next video.